It's Sunday morning, but Samida is heading into office because she has some work that has to be done. Little does she realize what the day has in store for her. But something feels wrong the moment she steps into the office. She notices her boss's door ajar and walks across to see what has happened. Through the door, she sees her boss lying prone on the floor in a pool of blood. Completely horrified, she gingerly walks closer and realizes that he's not alive. In panic, she dials 100 to call in the cops. Welcome to another episode of the Maths Factor, where we try to demystify calculus by showing you how it connects to running races, roundworms and murder mysteries. Sounds intriguing? Keep watching. Back to Samida's office, where the police have arrived and are checking out the scene of crime. Meanwhile, Samida is sitting alone, coming to terms with the events of the morning, when things suddenly take a turn for the worse. A policeman comes in and starts questioning her. He asks her where she was last night. He figures that she did not have a good relationship with the boss. It suddenly strikes Samida that she is a possible suspect. She needs to produce an alibi. She is with 3 college friends partying till 4:30 a.m. But she's not sure when the crime was committed. She catches the constable and manages to get this information. At 10 a.m., the body temperature was found to be 85.6 degrees Fahrenheit. Then again at 12 p.m., it was 82.6 degrees Fahrenheit. The room temperature was measured to be a constant 70 degrees Fahrenheit. Using this, can Samida figure out the time of death? This could help her get an alibi and save her skin. Surprisingly, what Samida could use at this time is calculus. It could help her estimate the time of death. Before we figure out her calculus capabilities, whether she did or did not murder her boss, let's try and understand what calculus is. For that, we'll need to change scene to a racetrack. These 3 college students, Bisman, Hashmeet and Swati, are competing against each other to decide which of them will represent their college in an inter-college sports meet. The race is about to start. It looks close, but finally Bisman races ahead to win the race. Let's just freeze the moment to understand the mathematics behind the race. Now let's say that Bisman's close to Usain Bolt in terms of timings and has completed 100 meters in 10 seconds. Then we know her average speed is equal to distance by time is equal to 100 meters by 10 seconds, which is equal to 10 meters per second. Which means she ran 10 meters every second. Now this is simple arithmetic. What it does not give us is the speed at any given point during the race. Let's replay the race and study it in more detail. At the 50-meter mark, Swati is ahead. Bisman races ahead only after that. So what is clear is that Bisman's speed is not constant through the race. This is when calculus comes in. If Bisman ran at a constant speed of 10 meters per second, this is how we would plot it. However, since her speed keeps changing through the race, we can map it like this. Calculus can help us work out her speed at the start, the speed in the middle, where she races ahead, and the speed at the end when she wins. It can basically work out the speed at every second of the race. Now, this idea of instantaneous speed can actually be tracked back to ancient Greece and a philosopher called Zeno, who prided himself on curious and paradoxical situations. Let me tell you about one of them. This one involves an arrow. Zeno's claim is that an arrow in flight is always at rest. Curious, right? How can a moving arrow not move? It becomes easier to understand if we take a snapshot of an arrow in space. At that point, it is motionless. Since time is a collection of instants, the arrow never moves, which is clearly paradoxical, since the arrow is clearly traveling. Now let's move away from Zeno to the idea of calculus. From the race, it's clear that calculus is concerned with how things change. Here's another example. How fast your heart beats per minute at 7 a.m. compared to how fast your heart beats at 11 p.m. is an example of something that is changing over time. So calculus can come into play here. There are two main areas we cover in calculus: differentiation and integration. Very simply, differential calculus cuts something into small pieces to find how it changes. Integral calculus integrates the small pieces together to find out how much there is. Not so complex, is it? In fact, even these roundworms can do calculus. Wondering how that works? Take this particle of food. The intensity of the smell reduces as you move away from it. Now, from each position, the roundworm judges the rate of change of strength of the smell and decides its path forward or otherwise. This is equivalent to taking a derivative in calculus. Let's leave the roundworms to their calculus and take a break. But we'll be back to show you a magical way to understand circles, the famous battle between Newton and Leibniz, and we will figure out whether Samida is guilty or not. All on the Maths Factor.
राज्य सभा टेलीविजन की खास श्रृंखला महामहिम राज्यपाल में आपका स्वागत है।
स्वैच्छिक क्षेत्र है। ये लोकतंत्र का 5वां स्तंभ है। लोकतंत्र को बनाने में, लोकतंत्र को संवर्धित करने में, लोकतंत्र को सुधारते रहने में ये बहुत बड़ा काम है।
महामहिम राज्यपाल में इस बार गोवा की राज्यपाल मृदुला सिन्हा से मुलाकात सिर्फ राज्यसभा टेलीविजन पर।
Hello and a very warm welcome to a brand new edition of World Panorama with me, Frank Pereira.
Barack Obama has been elected on the basis that I will no longer take America into wars, and in fact quite the opposite, I will pull America out of wars.
According to the Indian government, fishermen are not at fault.
The US intervention in Iraq set the stage for exacerbation of these conflicts, and then the intervention in Syria.
Watch World Panorama at these times on Rajya Sabha television.
कागज पर उतरी रेखाएं, नेता के माथे चिंताएं, ब्यूरोक्रेसी तनी तनी सी, पब्लिक लेकिन खिली खिली सी, लेता है सबकी वो खबर, धारदार है इसकी नजर, नहीं बोलता ये किरदार, लेकिन सब हैं खबरदार, पढ़ने वाले का जीते मन, सिर्फ एक है वही लक्ष्मण। देखिए विरासत में इस बार आर.के. लक्ष्मण का कार्टून संसार।
Back in the Maths Factor, we're using calculus to help solve a murder mystery. Samida's boss has been killed and things are looking not great for her. The police have figured that she and the boss have a bad relationship and are wondering if this is motive enough for her to be earmarked as suspect. In panic, Samita calls her brother, who is an engineering student. She gives him the information she has. Her brother tells her that he will call her back in 5 minutes. She waits anxiously. Her brother announces that the time of death was around 3:52 a.m. Samita is flabbergasted. She asks him how he worked it out. Let's try and figure what he did. We knew that at 10 a.m. the body temperature was 85.6 degrees Fahrenheit. And at 12 p.m. the body temperature was 82.6 degrees Fahrenheit. Normal body temperature is 98.4 degrees Fahrenheit. Using the rate of change of temperature versus time, he works out that the time the person was killed was 3:52 a.m. What he actually used was Newton's law of cooling to estimate the time of death. Samita was of course so relieved that she wasn't really paying attention to the maths. Now, calculus as a discipline evolved in the 17th century. But the question as to who discovered calculus is a matter of great controversy. Before we get into that, let's go back in time to Greece in the 3rd century to visit Archimedes. Now, we all know about the story of him emerging from the bathtub with a triumphant eureka when he discovered the Archimedes principle. What you may not know is that he was so obsessed with mathematics that he would forget to eat. In fact, legend has it that when he was killed by a Roman soldier, he told him, "Don't disturb my circles," referring to the drawing of the circle in sand. Even his tombstone is marked with a figure of a sphere enclosed by a cylinder with a ratio of their volumes 2:3 indicated. We are now going to join Shivesh, a 12th standard student who has decided not to study for his exam, but to instead explore some pre-calculan concepts developed by Archimedes. He's going to work out the area of a circle. That's pretty simple. You have done it in school, right? So the formula for the circle whose radius is r is pi r squared. But have you ever thought how we come to this conclusion? To figure this out, Shivesh constructs a circle with 4 quarters. He then rearranges the quarters like this. Now, if we consider that the circumference of a circle is 2 pi r, then the length of the scalloped edge at the bottom is pi r, which is half the circumference of the circle. And this side is the radius of the circle, which is r. Now he constructs yet another circle with 8 equal segments. He then rearranges them to form this shape. Now if we look closely, we'll see that the collapsed edge at the bottom is looking straighter. Other than that, the length of the scalloped edge at the bottom is still pi r, and the blue side is the radius of the circle, which is r, is now a bit more upright. Now Shivesh constructs yet another circle with 32 segments and repeats the process. What he realizes is that the circle slowly becomes flatter and starts looking a bit like a rectangle. And as we break up the circle into more and more pieces, the shape becomes a rectangle. And just as before, the earlier facts are still valid. And so the length of the bottom of the width is still pi r. And the length of the side, which is equivalent to the radius of the circle, remains r. Now the area of a rectangle is nothing but its length into its width. So the area pi r into r is equal to pi r square, which is nothing but the area of the circle. Happy with this result, Shivesh starts studying again. Now the method he used, which was breaking up a figure into smaller, more familiar bits and adding them together, was actually a precursor to integration as we know it today. Let's take a minor break before we return with India's contribution to pre-calculus, which predates all Western discoveries. Join us in a minute on the Maths Factor.
Tradition dating back centuries. A cultural heritage that inspires and warms at once. Magic that awes. Rajya Sabha television brings you events that embrace the wonders of India's classical arts. Conversations with the biggest names in the culture and music. Rajya Sabha television, democracy at work.
शहीद भगत सिंह स्वतंत्रता आंदोलन के सबसे प्रभावशाली क्रांतिकारी। आजादी के दीवाने भगत सिंह ने नौजवानों को सिखाया, देश के लिए जरूरी हो तो जान पर खेल जाओ, मगर बेवजह किसी का खून ना बहाओ। क्रांति की नई इबारत लिखने वाले भगत सिंह ने कहा, बम और बंदूक नहीं, विचार लाते हैं इनकलाब। इंसान मरते हैं, विचार रह जाते हैं। जो देश के लिए जीते हैं, मरकर अमर हो जाते हैं।
खबरों का संसार।
भारतीय समाज के ऊपर टेलीविजन का असर बढ़ गया काफी। मीडिया पावरफुल है।
गायब है सरोकार।
10-12 चैनल बड़े बड़े घरानों ने खरीदे हुए। प्रिंट मीडिया की एक सीमाएं हैं।
बाजार की मार।
टेलीविजन सेलिब्रिटी का निर्माण।
मीडिया कितना जिम्मेदार।
सब चीज बॉटम लाइन पे आ गई है कि उस पे इतना खर्चा होगा, उससे कुछ मिलता है कि नहीं मिलता।
देखिए मीडिया मंथन शनिवार दोपहर 12 बजे, शाम 7:30 बजे और रविवार शाम 4 बजे। A new government in New Delhi. New faces.
People are not investing because they are scared of your tax administration.
New thinking.
The auction process is a fair and good process.
You cannot have a one-size-fits-all reform policy.
For insights and perspective.
Judiciary should be more concerned about corruption within itself.
The Modi government slogan of अच्छे दिन आने वाले हैं. Soon the people's slogan will be हमारे पुराने दिन लौटा दो.
The biggest show on economic policy. Watch State of the Economy.
On the Maths Factor, we are exploring the intricacies of calculus. Before we delve into the history of the subject, here's a question for you. What's the similarity between the Titanic and calculus? Well, calculus actually developed because of shipwrecks. One of the biggest reasons for accidents was the inability to navigate properly. Most ships used the stars to navigate. And there was little understanding of how the Earth, stars and planets moved in relation to one another. The development of calculus solved that issue. So calculus was useful for shipwrecks. But who really uses calculus in a daily routine? Let's look at a few examples. This is Pitambar Sani, an architect who's been commissioned to build a new university. He's contemplating a dome-shaped building. Now, he will need to use integration to determine the amount of materials necessary to construct a curved dome as well as calculate the weight of that dome and determine the type of support structure required. This is Veena Gupta. She opens a credit card bill and reads she has to pay only a minimum of 1,380 rupees, even though a bill total is for 30,000 rupees. Have you ever stopped to wonder how the minimum payment is worked out? Quite right, calculus again. Credit card companies use calculus to set the minimum payments due by considering multiple variables such as changing interest rates and a fluctuating available balance. Let's now head to Kerala in the 14th century to explore the work of a group of scholars that came to be known as the Kerala School. The founder of the school was Madhav. He came from the town of Sangramagrama in Kerala. Though very little is known about them, they developed a whole bank of knowledge in the area of pre-calculus, way before the Europeans even contemplated this subject. In fact, it is from these scholars that the first known calculus texts emerged. Now, what did these mathematicians do? They worked with infinite series, which is a critical idea in the development of calculus. Madhav showed how one can be expressed as a series where we add a half plus a quarter plus an eighth plus a 16th and so on. To see how this works, let's join Diksha, who is working with a wooden puzzle. It's square in shape. She puts in a triangle which is half the area of the square. She then puts in a smaller triangle which is quarter of the area of the square. She continues like this, putting in an eighth, a 16th, a 32nd and so on. But as we continue adding in fractions, the answer will come closer and closer to 1. Madhav also worked out that by successfully adding and subtracting different odd number fractions to infinity, he could hone in on an exact formula for pi. And through his application of this series, Madhav obtained a value for pi correct to an astonishing 13 decimal places. This series is today called the Madhav-Leibniz series. Now, these mathematicians also coined a fun way to remember this value of pi using a poem. First, let's take a look at the poem. Gods, eyes, elephants, serpents, fires, 3, qualities, Vedas, nakshatras, elephants, arms. The wise have said that this is the measure of the circumference when the diameter of the circle is 9 nikarvas. Sounds incomprehensible? Well, let's break it up step by step. First, there are 33 crore devas or gods, 2 eyes, 8 elephants, 8 serpents, 3 kinds of ritual fires, 3 gunas or qualities, 4 Vedas, 27 nakshatras, and 8 elephants again, and 2 arms. Now, if we arrange these numbers from left to right, we get the following number. What does the second half of the rhyme tell us? That this is the measure of the circumference when the diameter of the circle is 9 nikarvas. So we have the circumference, which is 2 pi r. Now, 1 nikarva is equal to 100 billion. And the diameter of the given circle is 9 nikarva. If we divide the circumference by the diameter, which is 2 pi r by 2r, we get the value of pi. And we do. This gives us the correct value of pi up to the first 11 decimal points. Pretty cool, eh? Some historians have suggested that the work of the Kerala school may have been transmitted to Europe via Jesuit missionaries and traders who were active around the ancient port of Cochin at that time and may have had an influence on later European developments in calculus. Which brings us to two of the greatest mathematical minds of Europe, the English Isaac Newton and the German Gottfried Leibniz, who both claim credit for development of calculus as a discipline. Isaac Newton needs little introduction. Considered one of the greatest scientists of all time, Newton discovered gravity and the three laws of motion. He constructed telescopes and worked in the nature of light. So who was Gottfried Leibniz? A prolific mathematician, he invented Leibniz's wheel, a very early version of a calculator. He eventually came up with a host of discoveries in the field of calculus. Now here's how the controversy arose. Newton started working in his theories of calculus between 1664 to 1666, but did not publish. Leibniz worked in it between 1672 to 1676, but published earlier. But because Newton was the bigger name, everyone wondered whether Leibniz had reached his findings independently or if he had stolen the ideas. Now what Newton developed was called his method of fluxions and inverse method of fluxions, which eventually came to be known as differential and integral calculus. What made Leibniz's work distinctive was a notation he introduced, which is what we use even today. In 1711, the controversy was taken to court. A commission was appointed by the Royal Society to look into the charges. Since Newton was the president of the society, it is not at all that surprising that Leibniz was found guilty of plagiarism. Eventually, the mathematical community came to realize that Newton and Leibniz had made their discoveries independently, but not until years after Leibniz's death. Well, that's all for today. We have journeyed through Europe and India, explored races and murders. I hope that calculus doesn't seem as scary as it did at the beginning of the episode. See you soon on Maths Factor, more magical, mystical and mad mathematics.